Good afternoon, and thanks for coming to the second tech talk on quantum computing. We will talk about image matching with an adiabatic quantum computer. And I'm very pleased that I'm being joined by Jordi Rose, who is the founder and CTO of D-Wave. And this company is pioneering the design and manufacturing of adiabatic quantum chips. Before we get to explaining how this works, I need to still go through one piece of theory that we haven't covered in the first talk, and this is decoherence. I also wanted to use it as a quick reminder what we learned last time. You might recall that the base principle of quantum computing, at least in the gate model, is that you have a state, and here's this 1, 0, 0 state, and you push it through a gate and get some result which you measure. Now the gag, so to speak, with quantum computing is that you don't only have to take this one state, but you can create a superposition of states. And this is still, even though it contains 8 base functions in this case, it is only one physical state. So with one clock cycle, you push these 8 functions through the gate, and the gate operates on all of those. And you learn that we can extend this game to, let's say, n qubits. And then again, with one clock cycle, one gate operation, you would operate on 2 to the n states. Unfortunately, and this is why we need to learn about decoherence, superpositions tend to be fragile. And decoherence is essentially the name for the process that destroys the superposition. That's why we need to study it to understand practical quantum computers. So decoherence, what it does, again, a qubit can be, or is typically a linear superposition of a 2-system state, here, alpha A plus beta 1. And we learned that the measurements you would get in case psi, the qubit, is in the state, would be alpha modulus square or beta modulus square. So your result would consist of probabilities. However, and this is very important to understand, a superposition is physically something very different than a statistical mixture. What is a statistical mixture? A statistical mixture is more like a shell game, where your state is either in state, or your system is either in state 0 or in state 1. You just don't know it. So probabilities enter because you have insufficient information, not of the fundamental quantum mechanical reasons. And decoherence basically is a process that takes a superposition and turns it into a statistical mixture. So the typical situation where this process occurs is where you have a system you're interested in, here your system S, and it's embedded in an environment E, typically much larger. So the formal element you use to describe the situation is called the density matrix. I will not derive it, just explain. Density matrix is used by quantum physicists to describe this situation, which typically are always in with real quantum systems. And the density matrix describes superpositions. These are called coherences in the density matrix lingo, and those are described by off-diagonal elements. So whenever those elements here are non-zero, you have superpositions. And again, these are the ones you need for quantum computing. And the guys on the diagonal, they indicate statistical mixtures. Again, this is not useful for quantum computing, called populations. And decoherence, now in a more formal way of saying it, is a process of destroying off-diagonal elements and only leaving diagonal elements. And this is the density matrix formalism. And here, one curious fact. Again, situation where we have a system in the environment, and the most general state, something slided here, is described by this expression. Essentially a linear superposition over those product states out of states of your system and your environment. And you might recall that those were always normalized, that the coefficients have norm 1. Then if you would, in such a situation, compute your density matrix, you would find that the elements look like this, and if you look how large are my elements, you would see it's bounded by this expression. And this expression, if you take a closer look, looks very much like a scalar product out of two vectors. And each of these vectors is not longer than one. So you have something like 2 unit vectors, and you try to compute the scalar product between those two vectors. Now what you find, and this is just a basic geometric fact, that if you take 2 normalized unit vectors, but out of a big space, and the environment has, let's say, m degrees of freedom, so this is the size of your space. So m can typically be very large. So in this situation, if you try this out with a little MATLAB program, you will find, or look into a math book, you will find that as m goes to infinity, the likelihood of your scalar product being 0 goes essentially to 1. So basically, simply by getting into contact with a macroscopic environment, superpositions disappear. At least this is sort of the traditional picture. However, now you might think, then it's hopeless. This is just the very general top-level view. What you indeed have to do to understand decoherence correctly, you have to look at the details of your system, how this works, and then we find there can be physical mechanisms that protect coherence. And this is actually the trick you need to employ to build actual quantum chips. And here I would like to hand it to Jordi.
Thanks.
And we have to do a quick microphone transition.
Thanks. Got 2 mics?
Yeah.
Excellent. Okay. So I was a theoretical physicist at one point, but I became what's more like a systems architect over time. And what I'm going to do is go back in time, back to when D-Wave was first started. And what I'd like all of you to do is imagine that you're going to start up a quantum computer company. And what you're going to do is you're going to be something like the CTO or the chief architect. So in that role, there are 2 big decisions you need to make. And often when people talk about quantum computing in the literature, the second one is what they talk about primarily, which is what are you going to build the thing out of? But there's one thing that's more important than that, and that's what computational model you will use. So in conventional classical computation, there's this dominant model that has evolved over time, sort of like the implementation we use of the Turing model, some universal model for computation, which is now embodied in the way that we build processors. In quantum computing, there are several equivalent universal models for computation, and you have to pick one of them. So one of the things I'm going to argue very strongly here is that it really matters which one you pick, because they're not all the same, and some of them are inherently better. And by better, I mean easier to build. So in this picture, I've shown two-dimensional chart. So in the columns, you have these computational models. And the one that is the dominant paradigm that consumes almost all of the literature is something called the gate model, which Hartmut touched on briefly. And the gate model is extremely well characterized. Many people have worked on it. It's not exactly mature as a field of study, but it's certainly the most mature field that quantum computing has from the theoretical standpoint. And what we do is not that. What we do is something called adiabatic quantum computing, and I'm going to describe in some detail what that is. The second axis, the second dimension, is the actual hardware you choose. And what we work with are materials called superconductors. And I'm going to briefly, again, describe why that is. But there are as many hardware ideas for building quantum computers as there are physical systems that people study in labs. So the idea, fundamental driving idea behind quantum computing is that you're using physics somehow directly to drive computation at its very basic and most fundamental. And as a consequence of that, really any physical system which obeys the laws of physics, if you can make it behave quantum mechanically and you can gain control over it, you can potentially use it as the basis for a quantum computer. Adiabatic quantum computation is actually a lot easier to understand than the gate model. It's in some ways much more intuitive, but it doesn't appear that way when you're first introduced to it. So there's some novel ideas in here that you kind of wrap your head around first before the simplicity of this comes through. So the basic concept is that in any quantum mechanical system, that's small enough in some way that you can formalize, you can write down an operator which is called the Hamiltonian. And in the last lecture, I understand that Hartmut introduced this idea. If you're not comfortable with the idea, just think of it as a matrix. So this H is some matrix that has some properties. It's Hermitian, it's self-adjoint for one. When you diagonalize that matrix, you get a set of real numbers, which are the allowed energies of the system. So in some ways of thinking about it, this matrix is just some object that describes what states and energies are allowed in your system. The energies are the eigenvalues, the states are the eigenvectors that correspond to those. So if you want to find those, all you have to do is diagonalize this matrix. So in some ways of thinking of it, quantum mechanics is nothing but a huge exercise in matrix diagonalization. The issue is the matrices are exponentially large, and so usually you can't just brute force solve Schrödinger's equation, which is the double-edged sword that you're trying to use actually when you build a quantum computer. So the way that AQC works is that you have a Hamiltonian, this matrix, that has terms that are functions of time. So you have a quantum system, and you somehow have knobs on your box. And you can turn these knobs and actually change this matrix. So think of a matrix with time-dependent coefficients. As you change these knobs, the eigenvalues of the matrix change. So what I'm plotting here are the lowest, say, 12 eigenvalues of some big matrix. And those numbers, those energies, correspond to the allowed energies of the physical system as I change these knobs in some particular way. So the idea behind AQC is that it comes from condensed matter physics originally, is that if you begin your evolution in the ground state, that is the lowest allowed energy, the system that you cannot do better than energetically at the beginning, and then you turn these knobs slowly enough, what will happen is you will always remain in that blue state. Now what it means to be in that blue state changes because you're actually changing the physics of the system. When you're at the end of your computation, when you go in and you read the bits encode the answer to the problem you're trying to solve. So somehow you have to make it so that the morphing of this Hamiltonian encodes the algorithm and the answer that you're looking to solve. Now that process is not simple, but there are proofs that show that this approach is universal, which means that any algorithm that you can run on a quantum computer, you can port to this way of thinking about things. Now one of the confusing aspects of this, even to experts, is that AQC, the way it was originally defined, is an exact algorithm. AQC fails if at any time you leave this blue thing, and that's just a definition of what it means to be AQC. There's a related model which allows you to not get the exact answer and still consider it a success. And this is called quantum annealing. And the idea here is you do everything exactly the same, you still turn your knobs, but you turn them real fast. And by turning them real fast, you lose the guarantee to always get the right answer, but you sometimes can get real good answers anyway. And one way to think about this is as a heuristic. So if you're familiar with things like genetic algorithms or simulated annealing or taboo search or any of these things, there are no optimality guarantees in these approaches, but sometimes they work real well, real fast. And when you just turn the knobs as fast as you can, you'll lose the optimality guarantee, but sometimes you get a real good answer real fast, and that's called quantum annealing. We have a little movie that we generated to try to show you what quantum annealing might look like in a very low-dimensional space. So here's a little movie. Okay, so imagine this thing here is this potential energy that your particle's sitting in, and imagine the ball is the state of your computer. So when you actually, I'm going to start it over again if I can without screwing things up. Here, watch as I screw it up. Okay, you start in the global minimum, so that's the lowest energy state, right? That's where we started. And then you morph, you turn the knobs of your Hamiltonian, and the energy changes. And the ball here got trapped in the wrong state. So this is more like quantum annealing than AQC. Quantum mechanics allows you methods to escape from these minima that are not classical. In that case, that was an illustration of tunneling under a barrier. So that if you were doing this classically, you'd get stuck up in that metastable minimum. But this annealing process that uses these quantum mechanical effects gives you pathways out of traps that you don't have classically. So this is a concept you can have when you think about AQC or quantum annealing. You have a surface, like a rubber sheet, and how you pull down the rubber sheet is your program in time, and where the ball ends up is the answer. And when you think about this classically, you've got this ball rolling around on this rubber sheet trying to find the lowest point, and classically it might get trapped, but in quantum mechanics there are pathways out of traps that you don't have classically. You can tunnel, do other variant things that use quantum mechanical effects. Okay, so that's a little introduction to AQC. The second thing I wanted to briefly touch on is why we use superconducting stuff over all of the variety of other approaches to quantum computing. And there's one clear reason. It makes this approach by far and away the best of all of them. And it's a real simple, pragmatic thing. It's the only approach that anybody has ever brought forward that you can actually build today using standard semiconductor processes. All of those other things that I showed you require technologies or fabrication concepts or infrastructure that just doesn't exist. So you have this long ramp-up process to bring up infrastructure. This stuff, and I have some chip, at least one chip downstairs I can show you, and I have some pictures that I'll show you later. You manufacture them in a standard semiconductor fab using absolutely common procedures. There's really no difference. You can get hundreds of millions of things on a chip without a lot of effort, just like you do in semiconductor stuff. So that's the main reason. Kind of a corollary to that is that these superconducting things allow you to build large devices, things that you can actually see with the naked eye, that behave as if they were quantum particles. And that has to do with the way that the physics of superconductors work. This is a well-known thing. It's well understood in the literature why this is. So there's other reason for doing this. One is that historically, people have always thought about using superconducting metals as the basis for very, very high performance processors. This traces back to the late 70s and an IBM project. The reason is that the physics of the devices operate over a very short time scale, so you can build extremely fast digital logic. There are devices that have been built that have operated at, I think the speed record was 770 gigahertz. So you can build ultra-fast clocks, you can build logic that operate at those frequencies, and you can run these small-scale circuits at speeds that you just can't get to using CMOS because of a variety of issues. The other thing which is related is that superconductors don't generate heat when you pass current through them. And what this means is that you can build ultra-low power devices, and in fact, you can do this in principle thermodynamically reversibly, which means that without any generation of heat whatsoever. Of course, you need to dissipate heat when you erase bits because of physics, but as long as you're not erasing bits, you can actually build, in principle, thermodynamically reversible circuits and operate with zero power dissipation. Okay, so we chose superconductors, we chose AQC, so now what? So you're the CTO and you've made these two decisions. The next thing you have to decide is what problem you're going to try to solve. So what we've done is we focused on applying the technology to the solution of this. The reason is that this was the easiest thing to build. There are all sorts of other things you could do, and we'll probably do over time, like factoring, like quantum simulation, like some other things. This just happens to be the lowest hanging fruit. So what this is a canonical binary optimization problem where you have a linear and a quadratic term. Those x's are zeros and ones, binary variables. How it works is that a user will present a vector and a matrix of real numbers. So the person who's writing the application somehow wants the solution to this, provides us with an H vector and a J matrix. And what we are attempting to return is the minimum E, that is a configuration of those binary variables that minimizes E. So if you forget all about quantum mechanics and about the details of what's going on, and you're just interested in the utility of the thing we've built, you can think of it as a black box solver of that. So if you can pose your core hard problem in this format, you can send it to us via this very easy to use web services type API. It gets sent to the processors, it gets crunched. This configuration is extracted from the hardware and sent back to the user. Yep?
So does the user get to choose J or both J and H?
So the question was whether the user gets to choose J and H, and the answer is yes. So H and J are both, can be chosen not entirely arbitrarily. I'll show you that there are some limits on this, but in principle arbitrarily, and in practice to some level of precision in both. You're sort of wondering why it is that we chose this problem. The answer is kind of neat. The optimization problem I just showed you is NP-hard, so it's intractable. There's no known algorithm that will give you a global optimality guarantee in polynomial resources. So it's one of these things that is mappable to a large number of different problems, fundamentally hard for reasons that are not easily solved or may never be solved. But it also is the formalism in which physicists describe a huge variety of physical systems. So that's something called the Ising model. So if you have a physics background and you take any stat mech, the Ising model is one of these things that you always learn about. It's kind of this pillar of the field where pretty much any system you can think of which has some local objects, they can be anything from heart cells to birds to spins or whatever, where you have some local property and some pairwise term. And what you're trying to do is find the behavior of that kind of a system. That can be modeled using this model. And so you've got this really, really hard math problem. And on the other hand, you have this fact that lots of physical systems actually have the exact same math. So what we were trying to do is build a programmable fabric. So imagine you have this grid of all of these things. And what we want to be able to do is create an analog version of whatever binary optimization problem you have by actually building the physical object that has the math that is identical to the problem you're trying to solve. So we're trying to physically embody your math problem programmatically onto a mesh of these devices to build this programmable fabric to be able to solve these types of problems. So the fundamental object from which this fabric is built is called a flux qubit. It's a very simple device. There's a loop of metal, so the outer big black loop here is what we call the qubit loop. This thing is interrupted by a smaller loop, which itself is interrupted by two devices called Josephson junctions, which are just weak links between metal leads, metal, insulator, metal. They're very simple. The device has three terminals, two in, one out. The two input terminals apply magnetic fields to the big loop and the small loop, respectively, via an inductive coupling. So these blue lines carry currents in proximity to the device, which generate magnetic fields, which couple into the device. The signal line out is a very sensitive magnetometer. It measures magnetic fields, which is fired. It's activated when the qubit is ready to be read out. And what that does is it senses the direction of the magnetic flux through this loop. This device is constructed and operated so as to only support two physical states in the regime in which we operate it. One of them is current, which flows counterclockwise around this loop. That's digital 0. And the other one is current, which flows this way around the loop. That's digital 1. Nothing else is allowed. So those two currents have magnitudes of about a microamp, give or take. And they are the two basis states in which the computation or the measurement is carried out. When you measure out the qubit, what you're doing is measuring the direction of that current via its magnetic field that it generates. This is a picture of what the physical qubit actually looks like. And you'll note that it doesn't look at all like the diagram I just showed you. The important thing here, which is another very interesting thing about superconducting qubits, is that the only thing that gives this thing its qubitiness is the topology here, the fact that this is a closed loop. You can deform these wires as much as you want under certain constraints, and it still is the same device. So that allows you, if you're an analog engineer, to lay out this metal in a way that gets you what you want in terms of the design of the fabric. So what we see here is, I'll just sort of trace around it. So if you start here and you go around this little transformer and that one and back to here, that's the big loop. This thing over here is the small loop. And the Josephson junctions are here. So this thing, this line here carries current in proximity to the big loop and biases it. So that's one handle in. This is the one that biases the CJJ loop. That's another handle in. And this here is the measurement device, the sensitive magnetometer that reads out the state of the device when you're ready. The other device that's very important is the thing that sits between qubits. So if all you had was a bunch of qubits splashed out on the page, it wouldn't be very useful for a reason that will become fairly clear. It's basically trying to solve the problem with the H's and J's with no J's. So if all you had are H's, it's stupid, it's very easy. So you need to have something that pairwise connects the qubits. So what this particular device I'm showing is one way to do that. You have a qubit over here on one side and another qubit over here. And in the middle, there's this structure which couples the magnetic flux from here and this one. And the trick is that by applying certain biases to this device, you can create a situation where it's energetically preferred for the two qubits to be in the same state, which is called ferromagnetic coupling, opposite states, which is antiferromagnetic, or zero. And you can tune that number, which is in effect the J in your Ising model, to a fairly high range. So in these units, say from 2 to -2 with a flat part around 0. So if you want to actually set a J between 2 and -2 in these units, you can just set it by varying your flux bias, the current on this line, to whatever number is appropriate, and it will set the coupling strength to be whatever you desire it to be. This is an optical photograph of the 28-qubit chip that we ran at the supercomputing demo a couple weeks ago. These little devices here are the qubits. They're the H's in your Ising model, the linear parts of the objective function. These liney things are actually small loops that you can't make out at this scale, which are the couplers, and those set the J's, the quadratic part in the Ising model. The way that you actually physically set these are via setting DC currents on these input lines. So each of these input lines sets an H or a J by setting a particular value of current. The way that the processor is designed, it's designed to enable this idea of AQC, or quantum annealing. And physically, the way that you do this is by programming the H's and a transverse term, which is related to the flux you put through the subloop, the little loop, on each individual qubit, and the J's programmed on the couplers. All right, so what do you do with this thing now to actually solve problems? So the way that we did it in the supercomputing demo, which is just one way that you can use all of these knobs. So each of these time-dependent functions is its own knob. So if you're going to program this thing at the level of machine language, the handles that you've got are choosing what all of these time-dependent functions are. So if you start at 0 and you end at like 10 microseconds or whatever, you can go in and define these wave functions, the forms of these functions, just time-dependent functions. There's 28 of them, and then a whole bunch that couple pairwise the devices. You go and you set all of those, you allow the thing to evolve, and then you get some answer. So the simplest way to use the system to solve this problem is you begin by turning off all of the H's and J's. You set them all to 0, and you ramp up the tunneling that, at every single qubit to the maximum that the physical system allows. So that's step 1. The second thing, and by the way, I have a whole bunch of slides that show how this works physically, and if there's time during the question period, I can go over it. The second part is to decrease the tunneling, which you can think of, if you're used to thinking of simulated annealing, think of it as a disorder. So you quench disorder, which is removing this term slowly. You ramp it down. That's quenching the disorder that comes from this term. Simultaneously ramping your H and your J's to their target values, which are given to you by the user. So those are the things that are defined by the application that is solving your problem. The third thing is you remove the disorder altogether. So basically you remove this transverse term, and what you're left with is a form that has a linear part and a quadratic part, and these sigmas are operators whose eigenvalues are the values of the qubit when you measure it. So they're +1, -1. They're binary variables. So when you read out the qubits, what you do is you select, you're basically projecting these guys out, measuring a set of digital zeros and ones in effect, which become the answer you submit back to the user. So the original binary optimization problem that had this linear and quadratic part, that's exactly the Hamiltonian at the end. So the energy of the physical system is in one-to-one correspondence with the problem you're trying to solve. And then you report back the answer that you got from the qubits, and that gives you the user his answer. Okay, so the last thing I'm going to describe is why we know this thing is a quantum computer. And the way I'm going to do that is by illustrating some basic physical principle that you can show at a single qubit, which is kind of the lead-in to the more complex theory. So I'm going to talk about one qubit, and then I'm going to make some statements about what happens at larger qubits without explicitly showing them. So the first thing I'm going to do is imagine you have a Hamiltonian which is not diagonal in the measurement basis. So what I mean by that is that in this jargon you have a sigma x Pauli matrix, which means that the off-diagonal elements of your Hamiltonian are not 0. They're in fact 1. This is very easy to do with the type of qubits that we've got. And all you have to do is set the bias through the middle loop to 0, and then set the bias through the small loop to a particular value, and you generate this Hamiltonian. So this is very easy to do. When you do this, what you find is that the allowed energies of the system are actually superpositions in the measurement basis. So what that means is that the circulating current things, which are the things I actually measure if I go in and measure it, are not physically allowed by themselves. So they're not eigenstates of the system, is a better way of saying it. So when the system relaxes to its equilibrium values, the two equilibrium values that it's allowed to have are both superposition states. So if I'm doing a quantum mechanical experiment, one of the things that people love to do is they'll take a qubit with a Hamiltonian like this and put it in one of those two states to begin with. So here I'm saying I'm going to initialize in one of the persistent current states. I'm going to make it so that I know that it's circulating like this, even though my Hamiltonian says that's not an eigenstate. So what happens? If you solve the Schrodinger equation, you find that in a closed system where there's no environment, what happens is you start to get oscillations of the probability. So if time is equal to 0, you have probability of being in the initial state 1, because that's where you put it. And then as time goes on, it goes to 0, and then back to 1, and then to 0, and then back to 1. So this is a well-known thing, this type of oscillatory behavior. Now, if you add an environment, you can't, it's easiest to think of things in terms of a density matrix in the way that Hartmut introduced. So in a closed system like the one I described, it turns out that this is the density matrix, where the diagonal elements represent what the state of the top left and the bottom right represent are the ground state and first excited state energies. So you have a half chance of being in both. Well, if the off-diagonal elements were 0. When you expose this density matrix to an environment and you integrate over the environment, which is a procedure that generates something called a reduced density matrix. So if you don't care about the state of the environment, you typically do this when you're doing these calculations. And what happens is, quite generically, you find that the density matrix becomes time dependent, and these time scales, T1 and T2, are known as decoherence times. And more specifically, T1 is a relaxation thing where you go from, say, a higher energy and you emit a particle and you go to a lower energy. Whereas this one here, dephasing, happens between states that have energies that are similar, which kills superpositions between them. So what happens very quickly in this case is that the system diagonalizes in the energy basis, and those are going to be very important words, where the number here and the number here are set by temperature. So you can think of this as a two-state system, and at 0 temperature, all of the stuff's in the bottom. As you increase the temperature into infinity, they become equally likely. So I'm just going to skip through here to this, which is the punchline. So now imagine after this decoherence process, you've got this diagonal thing, and then you say, well, didn't we just lose everything we wanted? Because we've diagonalized this matrix, and like Hartmut said, isn't it the superposition stuff that's the thing that really saves us, and don't we just have a statistical mixture now? In fact, this is exactly a statistical mixture, but the key question is of what? So when you look at what this really means, the energy basis, so the ground state and the excited state, are not the same as the 0, 1 states. And if you think about this geometrically, they're kind of rotated 90 degrees to each other. So when you take this matrix and you rotate it in the way that's appropriate, so that now what's on the diagonal are the 0s and 1s, whereas before they were the pluses and minuses, what you find is that you get off-diagonal terms which don't go away. They're equilibrium properties of the system. And so this is very important, is that the concept that most people have that if you take something quantum and you expose it to an environment, noise, heat, all that, if you wait long enough, it's going to become classical. That's wrong. That's only true sometimes. And there are examples where you can have where the long-time equilibrium limit of an open quantum system contains superposition and entanglement and all of the other wonderful things that we need to do quantum computation. So in this particular way to do things, time is not the enemy. It turns out temperature is the enemy. So when you're thinking about what you need to have in order to run this type of quantum computer, it's not the same as in the gate model. So in the gate model, there's a very short period of time, this decoherence time, and during that time, the system will go classical because of the way that you have to manipulate these gates. So the requirement to be able to do all of these gates puts some constraints on what you're doing to the system's Hamiltonian. And when you do that, it turns out that as an immediate consequence, after this decoherence time passes, the system is classical. So in order to fight that, you need to go in with control that operates much, much shorter time than the decoherence time and fix errors actively. You have to go in and do things. Active, feedback, a whole bunch of stuff. And just to give you a scale, the T2 times in these devices are at least microseconds, and in some qubits, they're much, much shorter than that. So being able to go in and control the devices on things, timescales that are, say, 1,000 times less than a microsecond, isn't physically impossible, but it's extremely hard to do active feedback on superconducting circuits, for example, with nanosecond timescales. It's just very difficult. But in AQC, you don't need to do that because the things that you're using to harness are these equilibrium properties, and what you have to fight is large temperature. So whenever anybody asks you like what the decoherence time of a qubit is, you have to say, well, what model are you working in? Because if it's AQC, it doesn't matter as long as it's short, it's under some threshold. So this is something like a threshold theorem for this, this type of stuff. So you might ask, okay, well, fine, are your qubits in that limit? And they are. So we've developed a set of tests that extract the parameters that you need to extract in order to show whether or not you're actually in the appropriate limit. We've done that. This is all published stuff. You can look at Hartmut's literature stuff, and you can have the full introduction to this. But we have a way to extract these things and show that we're in the right appropriate limit. So the last thing is just, there's another thing. All I've talked about is single qubits now. And there's an obvious question as well, as you increase the number of qubits, what happens to all of these arguments? And it turns out that the thing you need to do is keep the number of energy levels that are within the ground state of the system polynomial in the size of the problem as the problem scales. So think of it this way. Let's say you had 100 energy levels within temperature of your ground state. All of those will become thermal. So what that means is that you'll have equal occupation of all of those 100 levels. If you really need to have the ground state and nothing else, you've roughly got 1 in 100 chance of getting the right answer. So as that amount of encroachment on your safe zone increases, the chance of you getting the right answer goes down. And the question is, how do those levels pack as the problem gets bigger? So I don't know what the answer is in general, and no one does yet. But what I can say for certain is that with the systems we've built, we can actually measure the appropriate ranges. And what we've shown is that in all instances of the problems that we've run up to 28 qubits, the widening of these energy levels doesn't kill the gap. So what that means is that there's always a separation between the ground state and the first excited state. And what that means is that any result you have here is in effect equivalent to any result you have here. And you can operate these things as if there was no noise. And for those of you who are familiar with the gate model, this is a kind of passive quantum error correction, that you have a threshold under which you behave as if there was no noise. So this is in effect removing all of the errors from your stuff, shielding the system that you care about, which is this ground state, from all of the errors by an energy gap. So in our case, so far, there are no energy levels within T of the ground state so far. Now that's going to change. So this is my last slide. Can we operate, say, 1 million qubits in this way, which is what we ultimately want to do, more than this if we can? I think that the answer is yes, but I don't think it's going to look exactly like what I've showed you. I think that there are differences in the way that you encode information into these devices that will probably be required. The ways that you quench this disorder are going to change. And the key issue for me is not whether or not we can build this thing, because I think we can based on what I understand of the state of the art now in fab. The issue is this physics/algorithms issue, which is how do you make it so that the number of danger levels gets pushed away from the ground state, and the gap is widened as much as it can be so that the broadening doesn't hurt you as much. That's the key issue, and that's a difficult problem. By the end of next year, we're going to have about 1,000 qubits. So we'll be able to do a lot of things experimentally and in practice with these things that are novel. So we'll be pushing this thing into a regime where no one has ever been before. Even 28 qubits is not really all that interesting from the point of view of applications. You can do some proof of concept stuff, but it's not powerful in the way it needs to be to solve big problems. 1,000 qubits is starting to get close. So I think that that'll be somewhere around the crossover where we start to get real utility out of these things, and people who only care about the black box are going to be okay with it, and then try to push it to about 1 million qubits within 5 years. So I'm going to now hand it over to Hartmut, who's going to finish by describing the application we ran at Supercomputing 2007.
So you mentioned that your real problem is energy levels near ground state as these system sizes. Now, do you achieve that energy gap even when you have strong coupling between your qubits?
Yes. Yeah, the answer is yes. And in fact, one of the objectives of the hardware program is to increase the scale of the H's and J's. So actually increasing the strengths of those numbers. Of course, the H's and J's have to be compatible. So if the J's or the H's overpower one or the other, the problem is no longer hard. The hard instances are ones where they're about the same order of magnitude, give or take. But no, that hasn't been a feature that we've observed when we do the experiments on the small MIS problems, is that the gap remains consistently large regardless of the particular instance that we solve.
Okay, so how many qubits are you simultaneously?
We couldn't hear this question.
Repeat the question? Can you repeat the question?
It looks like in the device that you showed, you're coupling 2 qubits, or nearest neighbor qubits, but are you able to couple at longer distances, which is what you need to solve, for example, a full Ising model?
The connectivity of the qubits is up to the designer. So in the particular one that I showed, each of the devices is 3 connected. But that is just a feature of the particular architecture of that chip. The limitations to how connected the qubits can be are ultimately having to do with the fact that the bigger you make the qubits, the more noise is introduced into the qubits. And every time you couple a qubit to something else, you need one of those little wiggly transformers, which increases the perimeter of the qubit. So the chip that we've got now that I showed you is in the smallest coupling connectivity limit. It's still 3 connected and non-planar, but it's nowhere near as connected as the later systems we hope will be. It's in the minimum connectivity limit. But there's no reason why you can't build arbitrarily, not physically connected, but logically connected systems. This is sort of gets down into some issues about how we actually embed problems into the hardware. Maybe we can postpone that to later.
Okay, so I want to use the last minutes to explain some applications. And as I had said in the introduction of the course, this is an unusual lecture series in quantum computing in the sense that we want to look at it strictly from the perspective of synthetic intelligence. So what can we do in areas like pattern recognition or machine learning with this device? And here I'm showing you the algorithms that we showed a couple of weeks ago at the supercomputing show, which is a first example that gives you a flavor. Essentially what we did with it is image matching. And just to remind you, image matching is an NP-complete problem. And image matching, I think this picture here shows what it means. Image matching means you have 2 images and you would like to find correspondences between image structures that correspond to the same physical structure in the outside world. And in order to do this, you can set it up as an energy minimization problem where you basically try to solve your problem by minimizing this term, where you have one term that is responsible for making sure that what you are matching indeed has high local image similarity. And the second thing, if these are really the same objects, there should be some geometric consistency. It should not be completely wiggled up. So the second term here enforces geometric consistency. And now the name of the game is to map this problem onto the quadratic programming problem that Jordi has shown you, which the D-Wave chip is designed to solve. So how do we do this? Given 2 images, we find interest points, which you can basically think of. We look at the autocorrelation function of the image, and we look at local maxima of the autocorrelation function. Essentially, what this means is we find blobs and corners in the image. And then each interest point gets described by some feature vector. Here you can plug in your favorite type, SIFT feature. We like Gabor wavelets, but pretty much any well-known process of describing locally your interest point would do. And then in order to generate the term in the energy function that rewards image similarity, we basically take a scalar product between the feature vector extracted here at interest point I in the first image and the feature vector at interest point alpha in the second image. Now, to take care of the geometry, we look at pairs of interest points and generate a vector S that describes the relative position and other geometric relations between those 2 interest points. And then, similar as before, now we look the question is I and alpha, does this fit okay with the match I want to do between J and beta? And do they sort of move the same way or not so much the same way? So there we create a term here which is not as simple as a scalar product, but essentially measures how compatible would these 2 moves be. And then we plug this into an energy function that now has exactly the shape we would like to have. It is a binary quadratic optimization problem. And then these terms here generate the H's. These are essentially responsible for local image similarity. These guys here will become the J's you saw earlier, which enforce geometric consistency. And then we ship those over to the D-Wave chip via some web service. It runs the adiabatic annealing process, and then we get back some of the qubits will be in state 1, and some will be in state 0 if they get measured. The ones that are in state 1 are corresponding to the best set of corresponding points we can find. And just to be clear, I started out saying image matching is NP-hard. And last lecture I told you quantum computers are not known to solve NP-hard problems. So what I'm not expecting here is in this process to always find the best solution, but due to the effects, tunneling, and other elements we had, I can reasonably expect to get a much better solution than with any classical machine. And let's quickly take another look at the same problem, which might illustrate what we have done in a different way, maybe easier to understand. Essentially, what we have been doing, we set up an adjacency graph. Each vertex in the graph corresponds to a match candidate pair. So structure I with structure alpha in image 1 and 2. And I have, of course, a lot of corresponding correspondence candidates. And essentially what I do, I bring only those candidates into the graph if the basic image similarity is better than a certain threshold. And I create an edge between two match pairs whenever the geometric consistency is worse than a certain threshold. So essentially, guys who have an edge between them, they kind of want to go into different directions. They don't correspond to a nice, smooth match between image 1 and 2. And then the energy function you saw before, here in this graph theoretical language, what it does, all the guys, the qubits that come out as 1, essentially correspond to the maximum independent set. So this is the largest set of match candidate pairs that play well with each other, meaning their geometric transformation, there's one smooth transformation creating those correspondences.
Now, initially I thought we were trying to find the features alpha and beta, et cetera, that matched up the best, but it now looks as though we've got all the alphas and betas and we're trying to match up the alpha with the I and the beta with the J.
No, it's still the same. We try to find the I's with the alphas and the J's with the betas, but only those who will allow that are geometrically consistent.
Okay. Are you accomplishing this as a series of computations for each feature? Pair?
No, basically, if the chip would be large enough, if let's say I have let's say 128, let's say here in this equation, I have let's say 128 candidate pairs that where the image similarity is larger than the threshold. If I were to have a chip that has 128 qubits, I could in one sweep get the solution. Right now the chip has only 28 qubits, so we had to do a little bit of mechanics to break it down into smaller sub-problems. But this is only sort of at the current level. So if I would have taken less match pairs, I could have done it in one sweep.
So if you have n features that are matching at some rudimentary level, then you need n squared bits in order to test.
Yeah, or if you have n in your first image and m in your second image, interest points, then there are n times m pairs. Exactly. Now this is quite a big number, and therefore you have these simple constraints here, throwing out those that look right away that bad that you're not interested in to get it down a little bit. And that's also where you can see why the problem is hard, because you have n to the power of m mappings. So this is a huge number of mappings. And in image matching, we can never hope with our current mousetrap, meaning a server center, to find the best solution in all circumstances. Again, with this process, we can hopefully get much closer to the best solution. Okay, so we're pretty much out of time. I will leave the learning part for next time. This is the problem where I wanted to invite you to actually to help me map the training of a neural network onto this or other binary classifiers onto the D-Wave architecture. But since we are out of time, I leave this for next time, and just want to show you kind of one feel-good demo that comes up here. Essentially feel-good. Why is this so slow? We're not online. So yeah, given that we are out of time, I shouldn't mess with it too much. What I wanted to show you is a program which essentially does the image matching, but it is in a way that is very familiar to you. We have a little MATLAB program that performs the matching, but using the actual hardware. So the MATLAB program has a Java portion in it, or calls Java routines, which talk to a web service where, again, we discussed that what you have to do is you have to take an H vector and a J matrix. This is basically what I just explained. You will be reduced to, then I have to ship this H and the J to Vancouver, to the adiabatic quantum chip. It runs. I get sort of the maximum independent set, or the best set of matching pairs back, and then I can plug it back into my algorithm. But it's basically a MATLAB-based platform that we have to do all sorts of experiments. And again, image matching is the first one, and I think that machine learning might this might be probably a yet more interesting problem that one should try to map onto the specific chip.
In the example you gave earlier with the alphas, alpha betas, and i's and j's, what would correspond to the H and what would correspond to the J?
The J's encode geometric compatibility, and the H's correspond to image similarity. So the H is literally computed by a scalar product between the feature vectors. It's as simple as that.
Okay.
So yeah, maybe should have made sure that we are online, because obviously this program talks into a web service and seems like we are not connected. So yeah, would terminate the lecture at this point, and maybe in the beginning of the next lecture I will show this demo.
Is there a way, since the AQC method only may not find the optimal answer, is there a way to actually determine whether or not you got lucky and got the optimal answer, or is it just you never know for sure?
Yeah, often it's easy when you get your answer back to verify it in some fashion. Here, to do this in an automatic way in the image matching case probably wouldn't be easily possible.
So for maximum,
Theoretically.
for maximum independent set, there are polynomial ways to put bounds, something called the Lovax theta function. So you can actually compute say a lower bound or an upper bound for what the MIS could be. And then if you get a number that is that bound, it's guaranteed to be optimal.
Oh,
So it's not as good as you'd like, but there are ways to bound so that if you actually achieve a bound, you know that it's optimal. But in general, you don't.
So just from the theoretical sense, if it's NP, that means it's polynomial verifiable.
Exactly, yeah.
But not all NP-hard problems are in NP is the problem.
Right.
So
this was the image matching was said to be an NP complete, which would mean no be in NP.
the decision version is NP complete. So if you ask the question, is there an MIS greater than 5 or something like that, then that is verifiable, obviously, because you just get an MIS and you count. But if you have an optimization, the optimization version where you're asking for what is the biggest MIS, that's not, as far as I know, verifiable.
Or let's put it like this, I was thinking it more from the practical situation where you don't have ground truth data. If I would have ground truth data for the right matches between those two images, then it would of course be very easy for me to verify whether the solution I got back is correct or not. In that sense, it's indeed verifiable very cheaply. When I said no, it was more like typically I don't have any ground truth data for image pairs, but sort of if you talk complexity classes, if you were to have ground truth data, then verifying it would be cheap.
So let's say if somebody somebody wants to approximate how well, basically, this Apple, by saying algorithm, it looks like it's more chip dependent. So how this will work? Because basically I'm giving the chip a matrix and a vector,
Yep.
and I'm waiting for a result, right?
Yep.
So I mean, it doesn't look like an algorithm because when they define a bound an algorithm, they can say that the best case approximation that we have is this factor. Is it possible to also define such a bound on?
Yeah, probably. I should just mention that you don't only have the option of getting to the at the level of abstraction where you present the vector in the matrix. There's also an API for going in and actually fiddling with the machine language. So if you wanted to write your own algorithm, which is controlling these things over time, you can do that. So really, the hardware is extremely flexible. It's much more flexible than just the thing that I showed. You can do a lot of different things with it. Now, in terms of proving optimality with algorithms, that's notoriously hard for adiabatic algorithms. There's a huge green field of unknowns in terms of the theoretical performance of this type of approach, in the worst case.
Yeah, that's clear. But I mean, whenever it's a heuristic, sometimes people are trying to come up with some approximation factor that the best you can do.
Yeah.
What it is. That's my question. Is it possible to say?
I think so. And probably the way you do it is look at the way that it's done with simulated annealing, where you can get some bounds. You'd probably do the same thing here with the different disorder, the transverse field disorder instead of temperature.
But definitely will be cheap dependent, right?
No. No. I mean, all of these chips are. I don't know exactly what you mean. I mean, every chip like this is nominally identical because it just depends on your fab, right? As long as your fab is good, they're all the same. If you change the interconnect among the qubits, you probably will get qualitatively different behavior, but probably not quantitatively different behavior. Yeah, actually, that's a very good question, and there actually is a way that you can use feedback in these systems, but it's not obvious. So what you can do, it turns out that with this type of a system, let's say you start the system in a particular state, so you choose a bunch of zeros and ones, and that's your original state. If you run it, there's a sense in which you can never get a worse answer no matter how fast you go through this evolution. So there's a more or less a proof in the regime in which we can move that no matter how fast you go, the answer can only get better. And you can think of it like this. Here's the state that you started in, and if you go on this straight line all the way up, you're in the same state at the bottom. The only thing you can do is come down off that state. So anytime you're allowed to do a transition, you get a better answer. So what you can do is pick a random state, run it as fast as you can. If the state at the end of it is different than the one at the beginning, you have a proof that it's better. Feed that one back and repeat. And this is some kind of a probably stupid, but easy to analyze heuristic for converging on some good local optimum.
So it's kind of like instead of doing a smooth transition, you're just shaking things and
Yep.
randomly hit a better local minimum.
And every time you shake, you have a theoretical guarantee that you're not going to get worse. You can be the same. So when you actually do this, you can find that no matter what you do, you're always in the same state you started in, which makes it not very useful.
So going faster doesn't kick it up.
It doesn't ever kick it off the trajectory that is the state you started
It
in.
might just push it past one or something.
Yeah, you can curve down into these energy levels that represent better solutions, but you can never curve up.
All right, do you have plans to implement something like that?
Yeah, we've done something like that on some of the smaller chips. We're experimenting with all sorts of ways to operate these things. So the annealing schedule I showed is the sort of stupid, easy thing to try when you don't know any better. But because we have all of this control over all of these knobs, we're experimenting with ways that you can fiddle with the knobs, either by using feedback or by doing something that has some kind of structured randomness. So some kind of Gaussian flickering or something like that. It's very hard to analyze these things from first principles theoretically. So the approach we've always taken is try lots of experiments and see what works and then drive in that direction.
Okay, thank you.
In the images you've been matching, there are these little circles with lines through them. What are those?
These are actually a good eye. I don't know with anybody else. These are actually interest points.
Those are the ones that don't
surpass the threshold.
Exactly. These guys either didn't pass the threshold. Let's say this guy didn't find here in the flower picture anything that was similar enough local image-wise, or maybe it did, but then it didn't fit well with the correspondences established by these guys. So typically, if you switch off the geometric constraints and only look for image similarity, you will find a whole bunch. So the geometric constraint is important to weed it down and get only a few correct ones.
And how did you determine that those were features of interest?
There's actually a whole science behind it. There are various ways of doing it. Typically, you have what's called an interest point operator, and this checks for, as I say, little blob structures, little corner structures. Actually, well, sets of interest put a paper up that, let's say, compares 10 such approaches in the literature.
How do you handle image scaling?
Image scaling is actually woven in. I glossed over this portion earlier, but we, you might recall, we sort of when we compare this here, their image scale rotation is sort of taken out of the comparison. So if two pairs would sort of, the vectors themselves that connect them might sort of look rotated, but this is taken out of the actual comparison. Yeah, scaling, same thing.
So in the long run, is quantum chip, if someday it becomes something like Intel chip that everyone can buy, is going to be something which is, I mean, close to a real chip that we have right now?
The chips will be very, in fact, they already are quite similar in many ways to, you know, an AMD or Pentium chip, except they have very low levels of integration, but other than that, they're fairly simple. The big difference is this all needs to be put in a very shielded, cold environment. And so when the actual chip is the size of, you know, your thumbnail, but the actual machine is about 10 by 10 by 10 of refrigeration. So the actual system right now is fairly significant in terms of footprint.
But my point is, if we want to do the computation that we are capable of doing today, in the future, can we only do with quantum chips, or we need a normal chip, like the chips that we
Oh no, these things, you have to think of these things as accelerators. I mean, they're special purpose processors that do something very well. And so I think, you know, you got to think about these things as just this application-specific coprocessor. It sits off in the corner somewhere. It's really good at certain things, but can't do anything else. That's the way to think about them, at least in the short term. Is that if you have some important problem like a machine learning thing, and you offload it to this type of processor, it might be able to do something transformative and awesome, but you could never do even simple other things on it.
Does the decoherence, is that simply a physical aspect, you know, like 1 over r squared, where, you know, the neighboring magnetic fields, their potential to cause decoherence is, you know, proportional to 1 over r squared, the distance from the one that's being ruined, or is it some kind of other effect?
It's not that simple.
It's more like a complexity issue?
No, it's more like, imagine you have two boats on the surface of a lake, okay? And there's a wave on the lake, and the two boats are going up and down at the same time, okay? So think of that as like coherence, everybody's happy in the quantum world. Now imagine you got like a beaver slapping its tail somewhere and creating ripples on the pond. So those ripples will start to move the boats out of phase a little bit. Now imagine the beaver is some source of noise on your chip. It's an electron which is hopping back and forth for some reason.
Yeah, no,
or like a little spin, magnetic spin is rotating or something. So you have this lake, and there's a gazillion beavers all around the outside slapping their tails at the same time, and the boats start to jitter out of phase. So the time it takes for the boats to go out of phase is something like this decoherence time. So the more beavers you have and the harder they slap, the shorter time it takes for the thing to go completely lose its coherence. So
but it's really the temperature just very, very local to the quantum chips, or it's the temperature?
No, it's every physical system that couples to the the quantum system that you care about. So in a physical qubit, which has this magnetic nature, anything that's magnetic has this, say, dipolar coupling, it's 1 over r squared, to the flux that threads the chip. It's actually not 1 over r squared if you're too close to it, but there's some function of distance. And then you have capacitive coupling. So there's electrical coupling. If you have an electric thing that generates an electric field, there's an electrical capacitive degree of freedom of the qubit too. So basically anything that, if you were to write down the physics of the system, couples to the thing that you care about is a potential source of the wiggling.
And last one, does making the qubits larger, does that diminish the impact of these influences? Is it related to size and bulk?
So it's a very non-trivial question as to how the qubit size affects the noise. There are some theoretical models where when you increase the size of the qubit, the effect actually goes down, and it has to do with a surface volume to surface area argument. In practice, though, what we find is that the noise scales linearly with the perimeter of the qubit. So the longer you make the line, the more the noise is. And what that's telling you is that there's a source of noise that sits under the wire or in close proximity to it, so that when you you increase the perimeter, the noise increases concomitant with your increase. And that's been seen in other labs around the world also. So there's something in the chip itself, probably in the insulating layer, that's creating a noise source that is smallest when you can make the qubit as short as you can.
How long does it take to get the answer? So you give the probability of machine?
Yeah, so the total time from when the problem is submitted to getting the answer is about a millisecond with the 28 qubit chip. Of that time, about a microsecond is the actual annealing. So this picture I showed of starting at 0 and going to 1, where all these energy levels morph, that takes about a microsecond. The other time is taken by I/O, and a substantial portion is in chip thermalization. So it turns out that after you measure the qubits, you fire these readouts, heat is jumped onto the chip, and you have to wait for that heat to go away before you can do it again. And so about half that time is just taken up with waiting for the chip to cool down before you run it again.
Can you also solve ILPs using your chip?
Solve?
With your programming?
So the easy answer is that anything you can map to a quadratic binary optimization problem, the answer is yes. The issue, though, is that the mapping may cost you computationally. So let's say you have some problem and it's some kind of quadratic cost, by which I mean your problem when you start it requires has n variables, but it takes n cubed or n squared qubits. That's no good, because n squared or cubed, when n is 1,000, blows the number of qubits up way too much. So what we're looking for are these problems that are natively mappable into quadratic optimization problems like this without incurring some kind of polynomial costs.
Okay, shall we call it a day?
Thanks.
Thanks very much for coming.